Hi guys, welcome to another lecture in the series General Inorganic Chemistry. And today we're going to continue our discussion on chemical bonding. So firstly, we're going to recap bond polarity and electronegativity. So bond polarity is a measure of how equally or unequally the electrons in a covalent bond are shared. And so a nonpolar covalent bond is one in which the electrons are shared equally, like these diatomic gases, chlorine and nitrogen, right? So in a polar covalent bond, one of the atoms exerts a greater attraction for the bonding electrons than the other. And if you guys recall my analogy with the tug of war, literally one atom is pulling the other person, or the analogy has two persons pulling on a string, right? And one person is pulling stronger than the other, and that is synonymous with the polar covalent bond, where one atom exerts a greater attraction for the bonding electrons than the other. And if the difference in the relative ability to attract electrons is so large, then we have an ionic bonding resulting from that. And continuing this review, for electronegativity, we use a quality called electronegativity to estimate whether a given bond is nonpolar, covalent, polar covalent, or ionic. And of course, we know that electronegativity is defined as the ability of an atom in a molecule to attract electrons to itself, right? We just did that analogy, and it's related to electronegativity. And so the greater an atom's electronegativity, the greater its ability to attract electrons to itself, right? And so the electronegativity of an atom in a molecule is related to the atom's ionization energy and electron affinity. Check previous lectures if you are unfamiliar with these two terms, which are properties of isolated atoms. And so an atom with a very negative electron affinity and a high ionization energy both attracts electrons from the other atoms and resists having its electrons attracted away. Therefore, it is highly electronegative. So what we see here is that we can actually use the difference in electronegativity between two atoms to gauge the polarity of the bond, the bond the atoms form, right? So let's consider these three fluorine containing compounds here. So these numbers that we're looking at here is based on the Pauling scale, right? So the value for, of course, fluorine is the most electronegative element with a value of 4.0, right? So I believe you can check out the second lecture for these values here. So they're in the, arranged in the periodic table. So these are not random numbers, right? And so essentially we have two fluorine atoms, they have the same number, and so the difference between them is 0. And so the type of bond is a nonpolar covalent bond, as opposed to HF, hydrogen fluoride. The electronegativity number based on the Pauling scale is 4.0 for fluorine, as we just saw, and that value for hydrogen is 2.1, or the value for hydrogen is 2.1, and if we take the difference, it is now 1.9. So there is a difference in electronegativity, and therefore the type of bond we see here is polar covalent. So let's look at lithium fluoride here, and we have 4.0 minus 1.0, which is the value of electronegativity for lithium, and that difference is 3.0, and hence the type of bond is ionic, right? So essentially we can't really give you a scale to say if you get 1.0 to 2 it's this, because there are other factors at play in determining the type of bond. But the what I want you to get from this slide is the fact that how we know that a bond is either nonpolar covalent, polar covalent, or ionic is that there must be, in the case of the polar covalent or ionic, a difference in electronegativity. And for it to be a nonpolar covalent, there is no difference in the electronegativity, right? So in general, a polar covalent bond results when the atoms differ in electronegativity. So we may not be able to decipher if it's ionic or polar covalent, but we know for a fact that it's not a nonpolar covalent once we have a difference in electronegativity between the atoms. And just to get familiar with certain notations, to show the charge distribution, we're seeing here a delta positive, which is the common Greek letter D, right? And this is how it is written. And for the hydrogen, it's delta positive, and for the fluorine, that is delta negative. So in other words, the hydrogen is slightly positive and the fluorine is slightly negative, right? So that is how we represent charge distribution when we have a bond here and one atom is slightly negative and the other is slightly positive. Alright, so just to add some visual to this slide, right, we want to show here how it looks. And so the blue portion represents low electron density and the red portion represents high electron density here, right? So we have a continuum essentially, right? So for our fluorine, which is a nonpolar covalent bond and the difference in electronegativity is 0, right? It's essentially in this region here, right? In terms of the electron density. So it's, not very low, not very high, and it's in this region here. For our hydrogen fluoride with a difference in electronegativity of 1.9, this is how it looks. So we have the low electron density portion, which is, related to our hydrogen bond, right? And then we have the high electron density portion, which is the most electronegative element, right? So this is pulling electrons to itself, and it should be no surprise here that this is a high electron density on the side of the fluorine. In contrast now to the lithium fluoride, which is an ionic bond, right? That difference in electronegativity is 3.0. So here, we can see a distinct blue portion and a distinct red portion. And so, we have an ionic bond here, and we have this low density lithium area and the high electron density area of fluorine here in this red portion here. So that leads us now to our first question, which is, in each case, which bond is more polar? So we're comparing here boron chlorine or carbon chlorine, that's for A, and then for B we're looking at phosphorus fluorine or phosphorus chlorine, indicating each case which atom has the partial negative charge, right? So you might want to take a second here and you pause the video and then use the trending electronegativities which we have discussed to do this. Alternatively, you can just go ahead and select the numbers based on the Pauling scale and do the subtraction, right? But essentially, you should be able to have a general idea based on the trends in the periodic table. So pause the video and attempt this question. All right, so if you had that, well, let's just recap the question. Which bond is more polar? So if you had boron chlorine and phosphorus fluorine, then you are indeed correct. Good job. And though we're not seeing it here, let me just fix that. Oh, it actually is fine. All right, so I have used some random values here based on the trends on electronegativity. So for chlorine, I used 4. For carbon, 3, and boron, 2, right? Because we're saying carbon is more electronegative than boron, right? And so if we do a subtraction here, the difference in electronegativity is greatest with boron chlorine as opposed to carbon chlorine here, right? So we're saying that the difference in electronegativity is greater for this as opposed to this, right? And that is why we're saying that this bond is more polar than this one, right? And of course, the other question said, indicating which case which atom has a partial negative charge. So definitely on the halogens, we have a delta negative charge. So just to increase our knowledge on various terms, right? Another term that we need to be familiar with is dipole moment. So you might be wondering, how can we quantify the polarity of a molecule? So whenever two electrical charges of equal magnitude but opposite sign are separated by a distance, a dipole is established. And so to check it quantitatively, or to measure quantitatively the magnitude of this dipole, is actually called the dipole moment. And we use the Greek letter mu as seen here, right? So if two equal and opposite charges, Q plus and Q minus, are separated by a distance r, so this is Q minus Q plus, distance r, the magnitude of the dipole moment is the product of Q and r, right? So for our purposes, we're not going to go into this or do any example of any calculations. What we need to have is an understanding of the term dipole moment, and that it's a way to quantitatively measure the polarity of a molecule. And so this expression tells us that the dipole moment increases as the magnitude of Q increases and as R increases, right? So everything is directly proportional. And so the larger the dipole moment, the more polar the bond. So for a nonpolar molecule like fluorine, as we just saw, the dipole moment clearly would be 0 because there's no charge separation. And dipole moments are experimentally measurable, right? So this is how scientists actually measure the dipole moments, and well, not how they measure it, but they measure the dipole moments and how they are able to quantify the polarity of a molecule. So just to give an idea of certain values related to bonding electronegativity differences, dipole moments of hydrogen halides, right? So we have our hydrogen halides here. We have our bond lengths, right? So we can see here that the largest bond length here is related to the iodide, right? And in terms of the difference in electronegativity, clearly the difference is greatest here with the fluoride. And for the dipole moment, that is obviously very well correlated with the difference in electronegativity, right? And so it should be even clearer here that there is a link between the bond length, the difference in electronegativity, and the dipole moment by extension. All right, so let's look at the types of intramolecular forces of attraction, right? So just to look at the terms intermolecular attraction versus intra versus intermolecular attraction. So inter, as we see here, means between, so between molecules, right? Intra means within, so this is within the molecule. So the types of attraction that we know about are ionic, covalent, and metallic for the intramolecular forces, right? So that is the forces within the molecule. So we spoke briefly about metallic bonding. So just to further reinforce that point, for metallic bonding is a type of covalent bonding specifically occurs between atoms of metals in which the valence electrons are free to move through the lattice, right? So here we have our electrons and our positively charged metal atoms here, and this represents our metallic bonding. So this bond is formed via the attraction of these mobile electrons and the fixed positively charged metal ions. And so metallic bonds are present in samples of pure metal, elemental metals such as gold or aluminium or alloys, which are like mixture of metals, right? So this is where you have these positively charged metal ions and the mobile or delocalized valence electrons forming or metallic bond. And as we said, it's an intramolecular force of attraction. And so the difference here between intra and inter is that for intermolecular forces of attraction, they exist between molecules, right? They're actually much weaker than intramolecular forces, and they determine the physical properties of molecules like their boiling point, their melting point, their density, and enthalpies of fusion and vaporization. So even though they're weaker, they are significant because they help to determine these physical properties of molecules. So one intermolecular force that we need to be familiar with is hydrogen bonding, right? And so this is a special kind of dipole-dipole interaction that occurs specifically between a hydrogen atom bonded to either an oxygen, nitrogen, or fluorine atom, right? So we have our water molecule here, three water molecules, and our hydrogen is intermolecularly bonded to or oxygen here, right? So all of these hydrogens are interacting with the oxygen. All of these oxygens are interacting with a hydrogen, right? So just to distinguish here that we have an intramolecular polar covalent bonding going on between the hydrogen and the oxygen, and we have our intermolecular hydrogen bonding seen here. So as I said, it doesn't have to be oxygen, it can be nitrogen or fluorine. Essentially, a difference in electronegativity, a huge difference in electronegativity. So hydrogen bonding is a relatively strong force of attraction between molecules, and considerable energy is required to break these hydrogen bonds. As you recall, the boiling point of water is 100 degrees Celsius. So clearly we need a lot of energy to break the bonds. This explains the exceptionally high boiling point and melting points of compounds like water and hydrogen fluoride, as I said, right? Why is it important? Why are we even talking about it? Yes, we know about water and we want to know about the properties of water. And again, the properties are related to the intra and intermolecular forces. But hydrogen bonding in particular plays a very important role in biology. So, for example, within your DNA, right, it is the hydrogen bonding that holds your nucleotide bases together, right? So, in this case, the hydrogen bonding is between hydrogen and nitrogen, as well as hydrogen and oxygen, right? Hydrogen, oxygen, nitrogen, hydrogen, right? So this is the bond, the intermolecular force of attraction that is holding your DNA. Okay. All right. So it's actually very important that we know and understand hydrogen bonding. All right, so let's move on now to molecular shapes. So consider the Lewis structure for carbon tetrachloride seen here, right? And I'm missing 2 electrons here, right? So this is our Lewis structure for carbon tetrachloride. All right, so looking much better now, right? This is our structure. The Lewis structure is drawn with atoms in the same plane, right? So here I need you to imagine a sheet of paper. That sheet of paper is all in the same plane. It's flat, right? And that's how we draw a Lewis structure. We're not seeing any other dimension, right? Just one flat structure here, like a sheet of paper. However, the actual 3D arrangement has the chlorine atoms at the corners of a tetrahedron, a geometric object with 4 corners and 4 faces, each an equilateral triangle, right? So here, if we imagine that the carbon is at the center and we have the chlorine here, chlorine here, chlorine here, chlorine here of a tetrahedron, 4 equivalent faces. So this is a face, this is a face. The triangle is sitting on a face, and there's a face that we cannot see around the back, right? So we're not seeing the face that it's sitting or standing on, and we're not seeing the one that is facing the back. However, we're seeing this face and this face. So there are 4 equivalent faces for this tetrahedron, right? And so just imagine that the chlorines are at the edges and that the carbon is sitting in the center and connects with all four atoms, chlorine atoms. Because all of the bond lengths are the same, right? And all of the angles are the same, which is 109.5 degrees. And so just to reinforce here that an equilateral triangle is one with equal sides, right? And because we have equal sides, then all our bond lengths are the same. The distance between the bonds are the same. And this is a space filling model, right? Which shows how it looks. And if you are a student of organic chemistry, you may have been familiar with drawing it in this way, where you have the straight line suggesting that these two atoms are in the same plane, and the hash basically says that this chlorine is behind the plane, and that this wedge is coming towards you, it's coming out of the screen, right? So these two planes would be in the screen, this chlorine would be behind the screen, and this wedge is coming out in front of you, towards you, facing you, right? So we're saying here that how we structure, we draw it like this, and it seems like it's flat, but we're saying in actuality it actually is not flat. So continuing our conversation about molecular shape, we look at the shapes of various molecules and ions, such as the carbon tetrachloride that we just saw, which have a single central atom. So our single central atom was carbon for this example. And that central atom bonded to two or more atoms of the same type. So that is how we're limiting our conversation to one central atom, two or more bonds bonded to it. So such molecules have the general formula ABN, in which the central atom A is bonded to NB atoms, right? So let's look at some examples here. So for carbon dioxide here, it is a linear molecule, and A is basically carbon and oxygen is B, and N is equal to 2, right? As opposed to, these various other molecules, notice we have different shapes: bent, trigonal, planar, trigonal, pyramidal, and T-shaped, right? So essentially we have one central atom, right? One central atom, and then we have different things attached to it, which is the B, right? So B is oxygen, B is fluorine, B is fluorine. And N represents the number of B, right? So we have 2, 3, 3, 3, right? And they have various shapes. So for ammonia, we're saying that nitrogen is A, hydrogen is B, and the number of hydrogen atoms, N, is equal to 3. So the shapes of most ABN molecules can be derived from just 5 basic geometric arrangements, right? So just to look at this, so we have the linear, as we saw with carbon dioxide. That is basically a straight line, 180 degrees. We have trigonal planar, right? And that is like a triangle, 180 degrees, and they're all in the same plane. For tetrahedral, AB4, we have 4 things attached to a central atom, and the angle, as we saw with carbon tetrachloride, is 109.5 degrees. So for trigonal bipyramidal, right, we have like a triangle in the middle, right? and then we have these two bonds here, which forms the shape trigonal bipyramidal. So we have 180 degrees separating these two atoms, and we have 90 degrees separating the upper atom from these in the middle, right? And then finally our octahedral, and that is literally just 90 degrees. So we have 4 things in the center as opposed to the 3 in the center here, and essentially 90-degree angle between the and the middle atoms, and 90 degrees, so it's basically like a square in the middle, and this is like a triangle in the middle, right? And so AB2 is 2 here, AB3 1 2 3, AB4 1 2 3 4. For trigonal pyramidal, we have 5 things attached to the central atom, and for octahedral we have 4 in the middle, 5 6 things attached to the central atom. So essentially we're now going to talk about the VSEPR model, or the VSEPR model, to see if we can predict these shapes, right? So when A is a representative element from one of the S block or P block of the periodic table, we can answer these questions by using the valence shell electron pair repulsion model, right? So don't be intimidated by this fancy sounding terminology. It's really very simple, and we're going to go into it right now. So for the VSEPR model in general, each non-bonding pair, single bond or multiple bond, produces a single electron domain around the central atom in a molecule, right? So as usual, we try to find examples to explain what we're talking about. So we have our central atom here, which is nitrogen, right? And of course, we would have drawn our Lewis structure for both atoms here, or for the 4 examples that we're going to do, we would have drawn our Lewis structure. I would have identified our non-bonding pair or bonding pairs, right? And so each non-bonding pair, single bond, and multiple bond produces a single electron domain. So this is 1 electron domain, this is 2, this is 3, and this is 4. So we have 4 electron domains for ammonia. For ozone here, this is the Lewis structure for ozone, right? And essentially we have 1 electron domain here, we have 2 electron domain here, and we have a 3rd electron domain here. So notice here that a double bond is 1 electron domain. So we end up with a total of 3 electron domains here for ozone. For carbon tetrachloride, we have only bonded pairs, right? And so we have 1, 2, 3, 4 bonding pairs, so 4 electron domains. For water, we have 1, 2, 3, 4 electron domains, right? So again, each non-bonding pair, single bond, or multiple bond produces a single electron domain. So the VSEPR model is, or VSEPR model, is based on the idea that electron domains are negatively charged and therefore would want to be as far away from each other to prevent that repulsion. So essentially, electron domains try to stay out of one another's way. And so the best arrangement of a given number of electron domains is the one that minimizes the repulsions among them, right? So in other words, they're further away. The arrangement of electron domains about a central atom of a ABN molecule or ion is called its electron domain geometry, right? So here in this table, we see that if we have two electron domains, this electron domain geometry is linear and the predicted bond angle is 180 degrees. If our number of electron domains is 3, the arrangement of electron domains is trigonal planar and the predicted bond angle is 120 degrees. And if the electron domain is 4, the arrangement of electron domains or the electron domain geometry is tetrahedral and the angles, as we saw, is 109.5 degrees. If we have 5 electron domains, then our electron domain geometry is trigonal bipyramidal, and as we saw, we have two different angles, 120 because we have 3 in the middle, and then we have the 90 degrees here. If we have 6 electron domains, then our electron domain geometry is octahedral and all the angles are 90 degrees for octahedral. That is these angles seen here. So in contrast, and we're going to see it in the slide coming up after this, the molecular geometry. So please recall these terms. Electron domain geometry, which is what we just spoke about, and then we're going to look at molecular geometry in the slide coming up after this. So the molecular geometry is the arrangement of only the atoms in a molecular ion, right? Any non-bonding pairs in the molecule are not part of the description of the molecular geometry. Let me repeat that. We're only looking at bonds for molecular geometry. Any non-bonding pairs in the molecule are not part of the description of the molecular geometry. So that leads us now to this table, right? So notice here that in this column we have electron domain geometry, and in this column we have molecular geometry, right? And in some cases our electron domain geometry is the same as our molecular geometry. But what we need to keep an eye on is the non-bonding domains, right? That is the key for distinction of the electron domain geometry versus the molecular geometry, right? So when we have 3 electron domains, having drawn our Lewis structure, we would identify the number of electron domains. If it's 3, then for our electron domain geometry, then it's trigonal planar. However, if you have no non-bonding domains, it's the same thing, right? If you have 1 non-bonding domain and 2 bonding domains, then we have a bent structure as we see here. So there's no non-bonding electrons, so we have trigonal planar as the molecular geometry. And here we have bent because even though we have 3 electron domains, 1 is non-bonding. So we see our non-bonding electrons here, and so we have two sets of bond, 1 double bond, 1 single bond. So 2 electron domains, 1 non-bonding pair, and so the arrangement is bent. For 4 electron domains here, that is tetrahedral, right, as we saw, and if there is no non-bonding pair, as we see with methane here, then the molecular geometry is the same as the electron domain geometry. However, if we have one non-bonding pair, as we saw with ammonia, then that shape is trigonal pyramidal, right? And if we have two non-bonding domains, the shape is bent, right? As we see with water. So water is bent, has a bent shape. So here, what is important is that we know that there's a difference between electron domain geometry and molecular geometry. And there's a difference if we have non-bonding electron domains, right? So hopefully that is clear. All right, so in summary, we can generalize the steps we follow to use the VSEPR model to predict the shapes of molecules or ions, right? So step one is we draw our Lewis structure for the molecular ion, as we have seen, and we count the number of electron domains around the central atom, as we saw, right? So step two is we determine the electron domain geometry by arranging the electron domains about the central atom so that the repulsions among them are minimized. And our third step is that we use the arrangement of the bonded atoms to determine the molecular geometry. So we went through all of this, guys. So in summary, these are the steps, and that is what we do. So let's see if we can answer this question. Use the VSEPR model to predict the molecular geometry of ozone and tin chloride, right? So notice that there's a negative charge on the tin there, which means that we have gained one electron. Right, so go ahead and pause the video and try to answer this question. All right. And so the first step is that you're going to draw your Lewis structure of these atoms. Count your electron domain around the central atom. Determine your electron domain geometry by arranging the electron domain about the central atom so that the repulsions among them are minimized. And then the third step is that you use this arrangement to determine the molecular geometry, right? So those are the steps that you're going to use to answer this question. So if you got bent for ozone and trigonal pyramidal for the tin chloride, you are indeed correct. So note the Lewis structures for ozone, right? So we have one non-bonding pair for ozone on the central atom, right? So that is why that is bent. For the tin chloride, we also have one non-bonding pair, but we have 3 electron domains attached to that. And so we have trigonal pyramidal, as we have seen. All right, so that takes us to the end of this section, and that's pretty much all for now. Thank you so much for watching, and see you next time.